right, so 13.4. Okay, so we're going to cover arc length and curvature in this section. And arc length, again, like I was saying, should hopefully feel similar to stuff you've seen before. The curvature will be completely new and look like a big mess, but that's an important idea. So, if we have, so don't worry about drawing any perfect picture here. So if you have some function moving through space, in Calc 2 we talked about arc length for parametrically defined curves. I don't know if you remember that. But that's, again, all this really is, right? So you get some R of t. Again, I'll just abbreviate here. It's FGH, right? And so how would you find the length of a curve? Well, again, if you think back to what we kept doing in Calc 2, right? How would you do this thing in calculus? How would you measure this thing? Well, you approximate, right? And so now we have a curve moving through space, and so all we do is we think here's, right, this corresponds to some starting point, a t equals a. This is a end point when t gets to b. And so if you just break up the interval from a to b into a bunch of different pieces, then you can approximate your curve, your length of your curve with a bunch of straight line segments. Does that make sense? So you just put these straight line segments on here. And the distance between, the distance between 2 points is just, let me just call it this. I'm going to abuse notation here a little bit. D of s, the distance between those points, is just the square root of your change in x squared, right, plus your change in y squared, plus your change in z squared. Does that make sense? That's just the distance formula. If you moved so many units over in the x, so many in the y, and so many in the z, that'll be the change in distance, right? So your change in position is that. And so that's, right, straight lines measure straight line distance, right? The distance between 2 points. And so our length of our curve is approximately add these all up for each piece, right? And so without worrying about it too much, let's just say, so S, which I'm going to say is arc length, will become the integral from a to b of the square root of f prime of t squared plus g prime of t squared plus h prime of t squared dt. I suppose you could memorize that formula, that's fine, but you should also really think of this as the following. This is the integral from a to b of the magnitude of the derivative of r, right? If you take the derivative of r, it's f prime, g prime, h prime, so its magnitude is exactly that thing right there. And so, I'll put a box around this one. This is really how you should memorize that formula, a nice compact version, and then come up with the other piece if you need to on the fly. Okay, so let's do this one. So find the length of this function along here. So again, all you do is take your derivative, this case, it's very simple. What is it? No, derivative.
2.
2,
1.
-2, -1, right? Be careful. It's an easy mistake and completely destroys the problem if you do the wrong one, right? So, all right. So we get this, and then arc length will just be the integral from 1 to 3 of the magnitude of that guy. And again, you can memorize it as the other formula, the integral of the square root of f prime plus squared plus g prime squared, and so on, but I'm not going to bother. So the magnitude of that vector is just 2 squared plus 2 squared plus 1 squared, right? Square root of that. So it's square root of
3. About 9.
yeah, so square root of 9, so 3, right? Okay? So we get 1 to 3, that's 3 dt, and so that integral is just 3t, 1 to 3, and so we should end up with 6. Make sense? All right, now let's confirm something real quickly. So what kind of curve was this R? 2t plus 4, comma, negative 2t, 5 minus t.
Plus 3.
Yeah, it's just a straight line, right? That's the formula, right? A constant plus a constant times t and so on. And so if you move on a straight line, your arc length should just be where you start, the distance from where you started to where you ended, right? Because you moved along that straight line. So let's just confirm with this one that that's hopefully true. What's your starting point? R of 1 is 6,
Minus 2.
negative 2, 3. Oh, 1. Sorry, I got my numbers mixed up. 4. And then 3 gives us
10. Max is 2.
negative 6 and 2. Does that sound right? And so what's the distance? Well, I was going to call it d. So think of these as points now. What's the distance between those 2 points? The square root of 10 minus 6 squared plus negative 6 minus negative 2 squared, right? And then 2 minus 4 squared, and let's hope we got the right thing here. So we get what? 16. What is it? 16. And 4, and so yeah, that works out right? Square root of 36. All right, so that was unnecessary, but it's always nice to see that this thing that seems a little bit abstract corresponds with what should have been happening in reality. Okay, let's try one more here. All right. Actually, let's do this instead. Okay, so again, you suppose you're on some curve like this, and it starts off at some point A, right, t equals A. So now if you let time just keep changing and you say, okay, I'm going from, let me go like this. I'll call this A, but it really corresponds with t, right? So t equals A, and then you move to some arbitrary time. Think of it as time, it doesn't have to be. But you move to some arbitrary time. You should be able to measure that arc length, right? And then as that time changes, you should be able to keep measuring that arc length, right? And so you should get a function that gives you arc length over time. For all different times, and that's what S represents. So S, and I'll put S of t, so this is your arc length function. Right? Should be the integral from your starting point A to an arbitrary t I'm trying to decide what variable, I'll just use that. And then I need to switch my variable, right? I can't use r prime of t because I got this t here. So I'm going to use u instead. That make sense? But that'll be your arc length function. And so that'll give you the length of a function as you go from a to some arbitrary t. Oh, and let me also notice, what's the derivative of this function? So the derivative of an integral is
The function itself.
the function inside it. So the derivative of this should be the magnitude of r prime. Okay. So this is going to come into play a lot in the next part of this section. But for right now, let's just do that. And so let's do an example here. Find s for r of t equal to 2t, comma sine of t, cosine of t. All right, so this one's got a nice simple solution to it. What's r prime of t?
2 cosine.
Okay, good. 2 cosine negative sine. Does that make sense? All right, and then, so if I want to compute this s, right? So s is the integral from, let's just start at 0, okay? So find s starting at. Okay, so from 0 to t, magnitude of r prime of u. In this case, we don't really, the u won't come into play, but let's call it u anyways. So what do we get here? We get integral from 0 to t, square root of,
5.
right, so it's 2 squared plus cosine squared plus sine squared, right? Which is 4 plus 1, right? So this gives you the integral from 0 to t of the square root of 5 dt, right? And then what's that?
U.
Oh, du, sorry. I'm getting lazy. So then it's square root of 5 u, right? And then 0 and t, so square root of 5. Does that make sense? Okay, so for today, this is all I really care about. So let me mention one last thing, and we'll try to go over this again in a minute. And really, the idea isn't that we're going to do this a lot. The idea is that we know we could do this if we have to. So s turns out to be this, right? So you start at 0 and you go for t units, you get to this position. So what's t? Well, it's s over the square root of 5. If I took this and I replace my r with this s, okay, then I get what? 2 s over the square root of 5, right? And cosine and sine of s over the square root of 5. That makes sense? Cosine, oh, sine first. Sine of s over root 5. Cosine of s over root 5. Does that make sense? So the thing to take away here is just, this is going to be the same function, right? But now it's got a new parameter. It was parameterized over t originally, right? Now it's being parameterized over s. And the reason why this s is interesting is every time you move 1 unit in the direction of s, your arc length will move 1 unit. Does that make sense? So you've basically switched the time frame that you're moving along your curve. So originally you might have been zipping around some curve. Now we're saying by replacing it with this arc length function that we solved for, you're coming up with a new parameterization where you move 1 unit along your curve for every 1 unit of change in time. Does that make sense? And so this is going to be important when we want to talk about curvature, right? Because you just care about how that curve, the shape is, the the curve is bending, not how fast you're moving along it. And so by doing something like this, you're basically locking into the same rate of speed on every curve. And so then we can say what it means for one curve to be curvier than another curve. Okay? So we'll do that in the next section, or the next part of this section.